Hi, and welcome to Allen High School's discussion of solutions at the PreAP or 10th grade chemistry level. We're talking about the more quantitative aspects now of solutions, and there are many ways. We saw the solubility curves earlier. There are many different units that are used to describe the relative amounts of solute and solvent. We're going to focus in only on molarity at this point, and we, in general, call all of those terms concentration, kind of like the game, concentration, amount per volume. You may have actually seen on some of the bottles during labs, excuse me, a big capital M. And that big capital M stands for molarity. Molarity is the number of moles of solute per liter, and this is critical. It's not just the liter of solvent. As we saw earlier, we had the 100 grams of water. This time, it's the liters of the whole solution. We make these in a volumetric flask. So ask me to show you one. I have a whole bunch of different sizes. This is one of our most precise and accurate pieces of glassware we have, a volumetric flask. And so the formula is moles per liter. Now, you know how at this point mass to moles use molar mass. So you can certainly do this in 2 steps if you want to. Just show me your work. You'll see also, though, on your formula chart, we have the formula moles are equal to gram or mass over molar mass. So if in place of moles, we can put mass over molar mass, you can do it in 1 step. All right? And you are allowed to use that big capital M. That's why I tend to use an MM for molar mass. It's not in books, but I think it helps you keep those clear for a while. Or you can put moles per liter. Okay? So it is one of the most common ways of expressing the concentration in solution. All right, so if an increase in molarity, so right here it was just talking about a 2 molar, sometimes we would say molar solution instead of 2 molarity sounds kind of wonky if you ask me. So we say 2 molar solution. All right, if we increase that, let's say we had instead a 6 molar, we compared it to a 6 molar solution, we would say that is a more concentrated solution. If we added water to it or we had fewer moles, we would say that it becomes a more dilute, or we diluted the solution. Concentrated and dilute are really relative terms. There's no absolute value in which we'd say, okay, we're going to call this concentrated, we're going to call this dilute. It's a really comparative term there. All right. Now, I have a picture here. You may have it in your notes depending on the year that you are watching this, but I have a picture that shows us how we make a solution. And I really liked this one. It's from Flynn Scientific, and I think it gives some good details. And you really need to be able to describe how to make these solutions. So your first thing is going to be, frankly, it's going to be to do a calculation, because you have to know how much solid to weigh out. So you're going to weigh out the amount of solute that you need. In this case, it's a solid solute. Now we take our volumetric flask. Back in the beginning of the year, we talked about these. They have a single mark on the neck. Right? They're limited in what they can do, but what they do really well. All right? So we fill it, I don't know, a half or a third. The key is you want some water in here, just a little bit of your water. You add your solid or your solute in there. It goes right into the water. It doesn't get stuck to the bottom. You get it dissolved. You either stir it, or what this is showing is a magnetic stir. And again, if you ask in class, I'll get this all set up for you. Okay? Once that's all dissolved, then what we do is we add water until the bottom of the meniscus is on that line. All right. Now, there's one extra step that you may have to do between here and there. If it was an exothermic or endothermic dissolving process, you may have to allow it to cool or warm up if it got cold. More likely it's exothermic and you have to let it cool. And that's because volumes expand and contract with temperature, right? So if it gets hot, it's going to expand with temperature. And when it gets down to room temperature, it's going to contract and you won't have it at the line. All right. So let's look at these calculations. I think they're pretty straightforward. Okay. What we want to do when we are doing these problems is you want to list your givens. My volume is given as 500 milliliters. That decimal place gives me 2 sig figs. I'm going to be real honest with you. If I were to change these notes, I would write 500.00 because that's how accurate most of these volumetric flasks are. So we've got 500 milliliters. I need a molarity of 2.5 molar. And the question says how many grams. Now, the reason I really want you to list your givens is because one of the simplest questions on the test is also one of the most missed. And I think it's because people aren't listing their givens. So if you list your givens, you'll have a better idea of which formula we're working with. Now, I personally like to use the kind of the larger formula, the more full-on formula here. All right, my volume, your next step is to liters, so we can't have milliliters. And so I'd put 2.5 is equal to mass over molar mass divided by my 0.500 liters. And the molar mass of sodium hydroxide is about 40.00 grams per mole. So I would substitute that in there as well. And this describes pretty well how to make it, so I'm not going to go into that, talk about that anymore in any more detail. Let's go on to the next question. And all right, whoops. If I have 35.8 grams of lithium hydroxide, okay, so again, I want you to list your givens. Don't get sloppy. This is too basic of a problem to get sloppy. All right, I want you to get these right. So I have a mass equal to 35.8 grams of lithium hydroxide. It's dissolved in enough so that my total volume that includes both solute and solvent, it's my volume of solution, is 750 milliliters. And the question asks, what is my molarity? Well, list your givens. Your next step is to check your units. I have to have liters, so be a good idea for you to show me that work in dimensional analysis. I'm going to save time and just write it down. I'm going to then substitute and solve. So list your givens, check your units, substitute, solve. I'm going to put my mass over my molar mass. My molar mass of lithium hydroxide is 23.95. All right, and that is all over 0.750 liters. Okay, and if you did that math, you should get 2, and I've got only 2 sig figs here. So this is somebody who probably made theirs in a really big graduated cylinder instead of a volumetric flask. But I'm going to run with it. We've got 2.0 molar, or you could say 2.0 moles per liter would be appropriate as well. So let's do just this one more problem here. and we will be done. List your givens. Mass is 40.0 grams. It's a little tricky. This has an unknown in the denominator, and I know some of you really don't like those at all. 0.50 molar. And my question is this time is, what is my volume? So grams are okay. I can go ahead and put that in. So molarity is going to be my mass, which is 40.0 grams, over my molar mass. The molar mass of sodium chloride is 58.44 grams per mole, divided by volume. And in place of this molarity here, I want to go ahead and put the value. I don't know why I didn't substitute that in. It's a Friday night. My mind must not be moving too quickly. So it's 0.50. So let's first cross multiply to get that volume out. So let's get the volume out of the denominator. So I would have volume times 0.5 is equal to 40 over 58.44. So if I then solve for volume, I'd have volume is 40, 58.44. The opposite operation of the multiplication, if I want to get it to the other side, is division. So hopefully, I know that was fast on the algebra, but this isn't an algebra class. This is chemistry. So you should get 1.37 liters. Given the fact that I have 2 sig figs up here, I'm going to call that 1.4 liters as my final answer. Okay, so those shows you the variety of ways we're going to be using this formula. The next step is to actually use molarity. Because it's a double unit, moles per liter, we can use it as a conversion factor and revisit everybody's favorite, stoichiometry. Until then, this is signing off.